Hello everyone and welcome back to this course. So last class we were discussing about the net rate of reactions and exchange current density. We also saw that if you want to favor a particular reaction either forward or reverse, we have to accordingly tune the activation barrier. So lower it will be the activation barrier or more will be the rate of reaction, accordingly the respective reaction shall be favored. So let's go ahead and discuss about the Butler-Volmer equation, which basically talks about the net uh, reaction rate and the potential. So let's write for the Butler-Volmer equation, which talks about net potential and the rate. So we need to draw these figures first. Let's draw this. So this is our energy vertical. So instead of drawing like a curved shape, we are trying slightly going to make it more triangular so that we can put some numbers and form the relations. So let's try to make this triangular. Let me use the different colors. So this is at the equilibrium. Right. So this is my equilibrium condition where the reaction barriers for both the forward as well as reverse reactions are equal. So this is the, let me draw that as well. So this is my delta G reaction or delta G equilibrium, I can say. Same will be here as well, delta G equilibrium for both forward as well as reverse reaction. So we are considering single electron transfer process, O plus E, that gives R. So this is our forward reaction and this is the reverse reaction. So what is going to happen is, now we will be since we are going to favor one particular reaction, we have to tune this or rather change this reaction barriers. So if you want to favor a forward reaction, this will be changed to new state. So this will be like this, right? So this is our new state of the condition. Let me draw that one more time. Right, so it is going to overlap, and so displacement, as you can see, this is our disturbance that we are bringing. This is denoted by eta. Now eta is the over potential, and if I try to split this into two, this is one half, the other one half. This is basically NF1 minus alpha eta, and this is NF alpha eta. Now alpha is basically the transfer coefficient. We will discuss a little more about it when we proceed further. So let me write here, alpha is our transfer coefficient. Typically ranges from 0 to 1 and the approximate values around 0.5, and this eta is the difference between E naught and E operating. So let us say this is our E naught, then this will be E, here it will be E. If I extend this, this will be E. So if I convert this E naught and E in the respective energy vertical, this will be NF E naught and this will be NF E. F is capital, this is Faraday's constant. So let's now relate the numbers, few numbers. So this is our delta G2, delta G1 will be this one, and this is basically an F alpha eta. So we are basically, if I try to simplify this reaction and the representation, I can see that initially the system was at equilibrium, where the reaction barriers on the both sides or for the both reactions was same, that is delta G equilibrium. Now in order to bring the net current in the system, we have disturbed the system by basically shifting this operating potential from E naught to E, and that displacement is nothing but eta. So as we have written here, this is our operating potential, E naught minus E operating, and if I, since this is a difference in the over potential, this difference in the potentials, I can relate this eta to the energy vertical by introducing one more parameter called as alpha. So if I take the summation of these two halves, that is NF1 minus alpha eta and NF alpha eta, this comes around NF eta. So in other words, we have converted this difference into the energy vertical. So now we want to understand what is the net current flowing in the system once the system is diverted by a factor of eta. So let us go ahead. So we know our delta G1 is basically delta G equilibrium minus NF1 minus alpha eta, and what is our delta G2? It is delta G equilibrium plus NF alpha eta. Now let us introduce one more term, that is called as rate constant. Now this rate constant, which is denoted by letter K, is proportional to the reaction barrier delta minus delta G by RT. The unit is of this rate constant is per second. So per unit time, unit of K is per second. So how can I write for the forward reaction? So I can write K12 is equal to A12 e to the power minus delta G1 by RT. Now A12 is basically some constant of proportionality that we have taken, and rest of things remain same. So I can go ahead and write it, expand this for delta G1. So this is A12 e to the power. So let me write it, substitute for delta G1. So delta G equilibrium minus NF1 minus alpha eta by RT, right. So if I expand this term, I get A12 e to the power minus delta G equilibrium by RT times e to the power 1 minus alpha and F eta by RT, right. Let us call this first term as K12. This is at the equilibrium, this term. So let us call this as K12 equilibrium. So let me write it here. So times e to the power 1 minus alpha and F eta by RT. So that this K12, let me write it here, this is the rate constant for reaction, forward reaction at equilibrium. Okay. Similarly, For the reverse reaction or the backward reaction, that is 2 to 1, how will it look like? So, K to 1 equals K to 1 equilibrium times e to the power minus alpha n f eta by RT. Okay. So, we know current is basically charge per unit time, right, which we have already written dnf dn by dt. So, what is this dn by dt? So, it is basically k times Cr 0 comma t. So, this is basically the what is this Cr 0 comma t is basically concentration of the reactant. So, let me explain that here. So, if I take the hydrogen side and this is our bipolar plate, hydrogen is being supplied. So, we want to know this is basically, as we have discussed, this is your bulk concentration, whereas what is the concentration at the interface here? It is basically C0 T. So, when I say Cr 0 comma T is basically surface concentration at the interface at given time or at any given time or at a given time t. And in other words, this layer, as we can see, this is roughly around 5 to 10 micrometer thick. So, we are interested in finding out what is the concentration of the reactants at this interface. We are not interested, or whatever is supplied as a bulk concentration is different from the what is available at the interface or at the surface. So, that is the Cr0T. This is the concentration of the reactant. Let me write it here. This is concentration of the reactant at the interface. Okay, and this K is again your rate constant. Right, and how do we write this for rate constant K? It is A times K naught e to the power minus delta G by RT. So, this A is nothing but the area of the electrode and K naught, we will see that. So, how do we write for dN by dt? So, it is dN by dt equals A K naught e to the power minus delta G by RT Cr 0 comma T, right, and we know current is basically Nf dN by dt. So, how do I write it for the current at the anode? Current at anode, let us call it as I subscript A. It is Nf K12 Cr 0 comma T times A, and I can substitute for this K12 for the other things. It is K naught 12, right, e to the power 1 minus alpha n f eta by RT. So, this is for K12 and Cr 0 comma T NFA. So, I have taken NFA outside, Cr0T is also taken outside. What is left is K12. So, I have substituted for K12, which is K012 times the this parameter. So, let us go ahead and write it for the cathode. Let me use the other slide. So, current at cathode, or it is IC, is K021 e to the power minus alpha n f eta by RT C0 0T NFA, right. So, this is our cathodic current. So when I say current at the cathode, I don't intend to say that it is at the other electrode or the second electrode. It is the same current that is flowing in the reverse order. So we have still taken the only one electrode, and we are finding out the forward current, that is anodic current, and the cathodic current on the same electrode, on one electrode. So let's assume K naught 1 2, which is equal to K naught 2 1. Let's call this as K naught. This is only at the equilibrium, okay, at equilibrium. Let me write at equilibrium. So what will be our total current? Total current will be, total current or the net current will be I equals anodic current minus cathodic current. So let's substitute for both of these currents. So let's take K naught and FA outside. What we have here with us is C R 0 comma T e to the power 1 minus alpha and F eta by RT minus CO 0 T e to the power minus alpha and F eta by RT. Let's call this as equation 1. So we have substituted for anodic current and the cathodic current, and now let's say that at equilibrium this anodic current and cathodic current will be same, or in other words, net current, that is I, will be 0. So from 1, what we can write is CR 0 T e to the power 1 minus alpha and F eta by RT, that equals CO 0 T e to the power minus alpha and F eta by RT. So let's expand this bracket on the left hand side. So you can write CR 0 T e to the power NF eta by RT times e to the power minus alpha n F eta by RT, that equals CO 0 T e to the power minus alpha n F eta by RT. So if you can see this will go away, and what we have is CR 0 T times e to the power n F eta by RT equals CO 0 T. So I can write for at equilibrium again. So this CR 0 T is nothing but CR star, that is again the at the bulk concentration is equal to the surface concentration, and C0 T is equal to C0. So let me write this as, sorry, it should be only CR and CO. So you can write bulk concentration is equal to surface concentration for both the cases, right. So let's substitute this back. So we can write CR into e to the power n F eta by RT equals CO, right. So if I want to find out this value of eta, I can simplify this and I can write this expression as eta equals RT by NF ln of CO by PR. So in other words, if this eta, as we already know, it is E naught minus E or E operating. If this is greater than 0, if this is positive, so we get anodic current. So how this happens? So if this is positive, we get anodic current, or in other words, eta is positive in case of fuel cells, because as we see, if this is our fuel cell and this is our E naught, and if you are operating at any potential other than E naught, which is always less than the E naught. So, these are our operating potential. So, eta is always positive in case of fuel cell. So, we get anodic current in case of fuel cell. And how does this look like in case of, if I want to draw, this is the equilibrium, the curve. So, it will be deviated like this. So, this will be our eta, and so this will be our forward reaction will be favored, that is H2 giving 2 H plus and 2 electrons. However, if this eta, which is E naught minus E, is less than 0, we get cathodic current, or in other words, in case of electrolyzers, let me draw it here for the electrolyzers. So, this is our E naught, and if this is our operating potentials, these are operating potentials. So, E naught minus E is always negative in case of electrolyzers. So, in other words, if eta is negative, we get cathodic current, and if I want to represent this here, so this is our bulk, or rather at equilibrium it looks like this. So, when we are working in the electrolyzers, we are basically shifting it towards upper side. So, this becomes our eta. This is our eta. So, in other words, our reverse reaction will be favored. As we can see, it is, this will be our delta G2, and this whole thing will be delta G1. So, delta G2 is smaller than delta G1. So, reverse reaction will be favored. However, in case of previous case, we can see this delta G1 is much smaller than delta G2, and that is how we can say that the anodic current will be flowing in the circuit. So, let us write. So, at equilibrium again, this total current is 0, that implies anodic current and the cathodic current are same. So, let me write this equation one more time. So, I can say that it is Cr e to the power 1 minus alpha n f eta by RT is equal to C0 or CO e to the power minus alpha n f eta by RT. Of course, n f a cannot we have on both sides, which get cancelled. So, I can write this expression like this, and since we are working at the equilibrium, I can say, let us assume this CO is equal to Cr, or which is equal to C. In other words, the bulk concentration or the surface concentrations of these species, and they are same at equilibrium, and let us assume them to be C, and so like that we can write for the exchange current is equal to, this is your exchange current, which is NFA K naught C, right. So, this is the exchange current. If I take this area A on the, or if I divide this with the area, I get exchange current density. So, that is the your exchange current. In other words, if you are drawing no current from the fuel cell or electrolyzer, we assume that there is some current flowing across the interface of the electrode at a particular on one side only. So, let us say this is our hydrogen electrode. So, we say that both forward and reverse reactions are same, they have the same rate, and there is some current which imaginary flow across this interface, which is nothing but the exchange current and the exchange current density. So, we will stop here and we will take on with the next steps in the upcoming class. Thank you.